today's Astrobiology Insights, Tracing Life Across the Universe. Our speaker for today's session is Teddy Tribano. He is an aerospace scientist, astrobiologist, and co-founder of Space for All and Magnetic Space. So without further ado, I would request Teddy to start with today's session.
Welcome, everyone. I hope you are well. Ksenia, wonderful to see you here. And I appreciate everybody taking the time to visit with us here. I think it's important to understand, where life began and how it began, and even why. And I spend a lot of my days thinking theoretically, mostly about that, and it's led me to a few things, and I'm gonna start sharing my slides now. The the amazing part of where we are on this planet right now. And at 4.5 billion years, 4.6 billion. What's 100 million years here and there? It just fascinates the heck out of me that we've made it this far, and this is going to take a minute to pull up, I think. Let's see. Here we go. Can everybody see my slide there?
Yeah, we can see it.
Brilliant. Thank you. The I had a really good friend who was up in the Arctic with me over this past summer. Um, Many of you may or may not know, but I manage a research station up in the Arctic for the Mars Society. And what was interesting to me was uh, our definition of life kind of varies from where you are and who you are. But as I'm beginning to learn more about some of those triggers, right? What was it that created those first few moments um, of chemosynthesis? I'm fascinated with that. I mean, what chemistry was involved? What biology was a part of that? And as I've moved through this moray of detail and information, I'm pretty much decided that we might have actually begun at the bottom of a watery world, and we might have been a part of something similar to that. I I don't know, but I know that the work we've worked to do to determine that, and so here we are today. I'm trying to move my slides forward, so give me 1 second. I'm going to stop share and go back into because I'm presenting the wrong slide. I apologize. It's not too early here, so I appreciate you guys accommodating me. Good seeing you. You're brilliant. Where it is? There it is. There you are. Apologies. 1 second. People are still joining. Brilliant. We're just not allowing me to move forward and back. Apologies. Could be that it's just a really big file. Hey, Andy. Yeah, anybody jump in if you want to chat while I'm figuring this out.
So where's everybody from on the line? Might be kind of fun to hear where folks are calling in from.
That's a good idea. Let's do that. Yeah, just chime in, anybody here, and don't worry about speaking over someone.
Seattle.
Yeah. CTAC. Let's see if this works.
Portland, Oregon.
Who's that?
Rachel Tillman.
Hey, Rachel.
Hey there.
Hope you're well. Yeah, I can see my slide, but it's not allowing me to go in the presentation mode. Maybe it will if I do this.
What format is it in?
PowerPoint, and I'm in.
Does it have any animations in it?
Animations meaning pictures, yes.
In your slides, no moving animations?
No, I didn't. I like to do that, but I didn't do it this time.
If you save it as a PDF, it'll compress the file and it might make it easier to present.
You know, I wonder if that's part of the problem.
Yeah, I mean, if it's too big a file, sorry.
Yeah, it is quite
Get
large.
little computer geeky here.
It is a very, there you are. Save as PDF. Let's save it and download. Save. Okay, let's see if that works. Awesome. Good idea. Oh, neat. Yeah, it did save it like that. Neat. Problem is, it's not populating in my tabs.
Are you downloading it from a Google Drive or is it on your local system?
No, it's local. Yeah. It is crazy slow right now. Weird. And I think it's probably because it's so many big images.
It might take a bit for it to actually save if it's huge.
I actually think that's exactly what's going on.
It takes a while for it to render the images in a PDF when you do that. It takes a few minutes.
Yeah. Okay, well then let's open that up and see if it pops. Good one.
So how many students do we have on the line and researchers? Maybe people can raise their hands if they're too shy to speak up.
Yeah, jump in.
Any students on the line?
Oh yeah.
So you have four students, is that right? 5 students? 6 students. Cool.
Hey,
How about
yeah.
researchers? How many other researchers? Got 1 researcher?
Okay, I think this is gonna work. Good one, Rachel.
Fingers crossed. I'm not familiar with this platform, so.
Yeah, I am, and I'm just shocked that it's. I think it's just because they're AI assistant to who. So hey, present now. Let's see if that works. And when I go to present, I pull up the PDF. There, crossing fingers. So weird. It's not allowing me. Apologize. It's not allowing me to move the file. Oh, we lost Theron. Apologies, Theron.
Terry, if you can mail this to me, then I can try sharing this.
Sure.
Yeah, I'm giving
Is
the mail
it
ID in the
the
chat.
is it the email? Yeah, put your email in there, and
Yeah.
I'll do that. Thank you.
How did you get started in astrobiology, Terry?
Good question. I spent better part of 10 years really digging into and um, learning particle physics, and as I got through the particle physics, I started to realize there is so much more in that's small, right? That I couldn't understand why we weren't digging further into that. And of course, when we found the Higgs as kind of the missing mass, that to me was kind of the beginning of diving deep into all things small. And here we are today. So anyway, all right, I am going to attach this file, hopefully, on the computer. Oh, there it is. If I give you the PowerPoint, do you think that'll work, or do you just want the PDF?
No, just share me the PowerPoint presentation.
Okay.
I'll
right.
try sharing
Cool.
it.
Awesome. Yeah. And it's taking a second to upload. Oh, there it is. Done. Wow, that was much faster.
It is
Okay,
more than
there you
25
are.
MB then.
Well, it will be, but
We've all been there.
yeah. See if you got it.
Yeah,
But
yeah,
I did just
let
send
me
it.
check.
Yeah, and then I started down this rabbit hole of the Krebs cycle. I don't know if people are familiar with the Krebs cycle, because I didn't understand why cells themselves were, failing, turning into cancer, and uh, and then you'll get a kick out of this, Rachel. It moved into uh, electromagnetism, and what powers cells and mitochondria, because really, right, that's at the bottom of why cancer happens, as you well know.
Passive energy.
Yep. And so, and it was this fellow by the name of Nick Lane, who I read a couple of his books now, over the past 3 years, 2 years. And man, oh man, it was just like a light went off. I was like, oh my, here we are. It's all about how a cell works together. Harshi, go ahead and speak if you have something on your mind there. And so to your point, right, the rabbit hole of astrobiology was just constant. It never ended. Oh my God, that's beautiful. Thank you. I think if you enable editing, it might let you flip through it, but otherwise,
So do you need me to change the slide?
If I can change them, that would be awesome.
No, you'll not be able to change it. I will.
Yeah. No, that's a good one. You can go to the next one if you want.
Okay.
You're very kind to help. Thank you. There you are. Boom. Your question, Rachel. Ask the questions. Yeah. Andy knows that rock really well. we stumbled on that stone up in the Arctic, and it's a stromatolite. It's likely in the hundreds, if not older, millions of years in terms of its age. We weren't allowed, and we agreed not to move it. We did geotag it, so we know where it is. But at some point, I'd love to get just a tiny little piece of that and get to know it a bit more. Stromatolites themselves are probably the original cyanobacteria fossils, and they go back. Some argue that it goes back to 3.4 billion years, and I wouldn't argue. For the most part, the Straley Formation, which is in Australia, the Straley Formation is probably in the 2.7 to 2.4 billion year range. But there's arguments, as Pangaea was breaking up and moving around. Pangaea was kind of the original landmass of Earth, and as it was breaking up, moving and migrating to all its different spots, that Greenland was originally down in kind of the tropics. And Greenland also, there was a stromatolite found in Greenland. And I'm like, wow, here we are. This is evidence that, that Pangaea happened, that stromatolites were forming, these cyanobacteria mats kind of are indicative of periodically, and each little line in the stromatolite has a story to tell in between the cyanobacteria that is fossilized, and that that's more than an encyclopedia of information. Fascinating to the end, and I can't wait for the Nunavut community, which is up in the Arctic, who kind of own all of the land and manage all of the land up in the high Arctic. Now, we were just below the North Pole. We were about 600 miles below the North Pole, between 600 and 700 miles. So the point of astrobiology really is digging into where we might find these little markers, these chemical markers, these biological markers of how life might begin and extant of Earth, and that should fascinate all of us, right? And we've all been asking that question most of our lives. Probably most scientists have. I'm sure lots of other people. But we can move to the next slide if you'd like, and I can kind of talk about and so what I wanted to do is I wanted to kind of map out Earth's early history, because the only analog that we have that we can discuss astrobiology is what we know now, and what we know is the only place we know that harbors life is Earth. And Earth was probably a bit hellish as it goes, and when I say hellish, I mean there was no way that life would have propagated in the environment of early Earth. And so in that kind of, in that, they call it the Hadean age, Hades is where that comes from. And that's the 4.6 billion to 4 billion years. We had the moon form, and the moon apparently, I think most people now would argue, would agree and not argue that Earth and the moon were originally just one big blob of molten mass, and we were struck by another very large direct hit, and that would have caused that little bubble to form and remove itself, and we were lucky that at that point that it was where it was. Early on, and most people don't know this, but when that happened, the moon didn't just land right in the same spot it is today and move 3 centimeters a year. It was much closer to Earth. It would have been in this image as you see it now, it would have been very close to Earth, probably within the hundreds of thousands of kilometers or less. And and so that late heavy bombardment kind of might have been all of those those little pieces of life elsewhere, right? Those little chemical signatures that we need for things to glue together and form early life. And in my case, I'm a very big believer that early life was the cyanobacteria. And so here, it's kind of going down the line, right? We had the Archean, and that was indicative of probably only a cyanobacteria, or a bacteria that created oxygen from really heavy concentrations of carbon dioxide, thankfully. And and as an aside, the extinction events that we all experienced, not we personally, but Earth, there were 6 of them, and some argue there might have been 13. I would say there's between 6 and 7 extinction level events, and these were mostly from really large volcanic active regions on the planet that caused snowball Earth, that caused, there were Chicxulub, there were all the other really large asteroids that struck up in the Arctic. Andy was there with me last year. The Arctic was hit by something incredibly large. I wouldn't think that would have been an Earth extinction event, but it certainly would have created some havoc had you been there at that time, and even anywhere on Earth at that time, because the crater itself it's massive. It's 20 kilometer by 12 kilometer. And that's probably one of the larger, other than Chicxulub, on the planet. And so these first prokaryotes were probably single cell RNA. There were no mitochondria. There was nothing inside of those cells that were allowing life to replicate as we know it. But these single cells were creating these oxygenated environments, and all of a sudden we went from really low oxygen to really, really high oxygen. Everybody knows here probably that too much oxygen is bad for you. And so, nitrogen started to be our balance, and carbon dioxide started to be a part of that. And here, this evolution of oxygen was likely kicked off by these early cyanobacteria, these prokaryotes. And here we are. I'm endlessly fascinated with stromatolites, and so I'm hoping at some point we have really good data on that one that we found. We can change to the next slide if you like. Thank you. Oh yeah. So again, kind of moving through the great oxidation, they're calling it here. It was oxygenation as well, and the levels went from 0 or really, really low to 30s and 40%. And now everybody knows we're at 22.5% approximately oxygen. But in that era, or in those epochs, from 2.5 billion to 541 million, there was still very little evidence of fossils or fossilized evidence that gave us an indication of what was happening. The only thing that we found that we can't really say, that we can't argue against, were these stromatolites. And you're going to hear me say that a lot, and I apologize, because I think that's probably one of the key indicators of how we evolved. We had a snowball Earth, and that was between 720 and 635 million years ago. That was coined by a colleague down in University of California, Pomona, UCal Pomona. His name is Joseph Kirshevik, and Dr. Kirshevik was a very big believer in the snowball Earth theory, likely because of these bombardments, these volcanic, all the volcanic activity that we had for those epochs, and very helpful, right? Because we needed all the sulfuric acid, because that's the only way you can get CO2 to oxygen, is having a combination of those two, sulfuric acid and CO2, and now all of a sudden you get the oxygenated environment. It's much more complicated than that, and many of you may even know about that chemosynthesis. But that would explain how oxygen began to form. And so the Edikarin. So the Ediacaran or Edia, you'll hear people say it sometimes, was also when we only still found multicellular prokaryotes. The eukaryotes really didn't show up until about a half a billion years ago. And we're all descendants of eukaryotes. And so the question remains, right? And it hasn't really been answered. And it's this massive gap in time. So we really went from 2.5 billion now to 541 million years. 2 billion years of who knows what was going on. And I think that's why astrobiology began to fascinate the heck out of me. Because now you look at Mars, Titan, some of the other moons of Jupiter, Saturn, Enceladus is beginning to really fascinate the heck out of me. I'm, I'm, I think we're seeing these analogs of life and perhaps how they grew. We've got, the Europa Clipper mission that's coming up. All of these I'll be talking about here in a couple minutes. We can move to the next slide if you'd like. Yeah, go ahead, Kushi.
Sir, you said about good morning, sir. Can you hear
Yeah,
me?
yeah, of course.
Good evening, sir. Sir, you talk about Mars and the Titan and the moons of Jupiter. What about Venus? Like Venus have
Yeah.
thick atmosphere, and it is said that we have found biosignature gas
thrive and then it would fail, and it would thrive and it would fail, and it's always money, of course. And I really hope that by the end of this decade, we're really spreading our wings, or our astro wings. So, yeah, you're
Yes, sir.
bringing up some really wonderful points.
Yes. Thank you, sir.
Of
Thank you so
course,
much.
yeah. Anybody, jump in anytime. These are deep, thoughtful conversations, and most of it's theory. So,
Thank you,
with the
sir.
exception of what we know about Earth, yeah. Ragad, go ahead. I
Hi
love your Titan.
everyone.
I love your Titan image. That's
Thank
excellent.
you.
Yeah,
I have the same question, but about Moon and Mars.
yeah.
Is there life for humans on Moon and Mars?
Well, we're going to the moon. I'm convinced. I'm on the list to go to the moon. I want to be on that list for the next several years. I think they'll allow me to fly up until mid to high 60s. So I've got,
Wow.
I've got. Well, when I say I'm on the list, they have to select me, and so that's the other issue. Is right. Most of us will never be selected for that, at least my lifetime. Um, yeah, I'd say the moon has a very little chance of having life other than what we've placed there. Um, yeah, and I think it's because it's outside of Earth's magnetosphere. Again, back to electromagnetism and magnetic fields, and what is the cycle of life, and how does that work with the Krebs cycle? What defines life? Y- the lunar surface is probably going to be the harshest place we might ever go and stay. Um, yeah, the solar storms themselves are just, you know, I think, and so the constant solar winds, and now we've got, and you guys are all seeing it recently. The solar cycle is off the charts. It's at one point they were saying, oh, it was going back to 2002. Now they're back to 1944 for kind of the most incredible strong solar cycle we've ever had. So yeah. And what was the other one? You said the moon and what else?
Mars.
Oh, well, Mars was probably alive at one time, right? We see the evidence of water. It's clearly there's hydrogenates there, and we know that we can get from clays, we can get water, and we're pretty sure that those clays are wet. That's about 10 cm underneath the surface of Mars, approximately 10 centimeters. And by the way, just so everybody knows, I teach a bunch of different classes, but one of my most intriguing classes that I teach is planetary science, and so we talk about Mars all the time. And I think it's because it's our next analog. It's probably the safest place for us to go. I know it doesn't have an atmosphere. Well, it does have an atmosphere. It just doesn't have the atmosphere that was conducive for us to pop outside and hang out and get some sun. But that's not to say that at some point somebody feels like it's possible to terraform. I don't see that happening, but you never know. Not in our lifetime, right? I heard a number. It was half a million or half a billion years if we were to really focus on it. Like, I don't think we have that time. I think we have 100 million years here on Earth, and we really need to, within the next several decades, we need to have some answers. As Professor Hawking's always said, right, the only thing that's threatening Earth more than anything outside of Earth's atmosphere is Earth itself, right? And you guys are all feeling and seeing that. So yeah, Earth, Moon, Mars, Venus, probably it in our solar system. But maybe Enceladus, maybe Titan. Titan. Oh my God, I have some really cool images here in a minute of Titan. It's that mosaic. I'm sure all of y'all have seen. But let's finish up on the Paleozoic, because this is when we started seeing life. This was that rapid diversification, right? Things started to multiply, and as fast as cells can multiply, oh my God, I heard a really cool. Hang on, Regan. Let me finish this one little thought, and then I'll get to you. If we were to if E. coli everybody knows E. coli. It's horrible, right? You get it, you're really sick, you might die. If we were to allow E. coli to replicate, if it didn't have a natural enemy, uh, which it does, right? It has all the other natural enemies, that sun and all those things that kind of kill E. coli. It's a really interesting thought experiment. If we were to allow E. coli to live freely without any natural defense mechanism, meaning that it was just going to survive as it is, nothing was going to kill it. We would have E. coli would be the number one eukaryote on the planet in, I think the number was 20 hours. 20 hours. And so, yeah, natural defense we need, right? And so going back to the Cambrian explosion and that to me, and in those early Permian periods, thankfully things evolved and life was it was like a boxing match, right? Everybody was all these little cells were fighting each other for survival, and we were and all along the way we're getting bombed by these crazy asteroids and solar storms that are stripping the atmosphere. There is one theoretical only, that a local star within X number of light years blew up, and when it blew up and then went nova or supernova, that it stripped our atmosphere. And that's probably what happened, but we don't know. We can only theorize these things. We can see some evidence of a really high radiation content at about 540 million years, which would explain kind of a stripping of the atmosphere that we thought we saw. And so that transition from early Earth, right, constantly being bombarded, to now the Paleozoic, and here we are. Really, this is where life started. So sorry, Regina, go ahead.
Oh, I just want to say thank you. I raised my hand accidentally.
No, good. Yeah, please, anybody jump in anytime. We could. Everybody gets an idea. This is a really cool image, because now we see sponges forming. We see underwater sea life starting to take shape. We see the sea anemone. Say that 10 times fast. I say 10 because sometimes I can say it 2 or 3 times, but that's it. So life was beginning, and it was probably beginning underwater. And because it was beginning underwater, we were limited to those they call them smokers, which were those underwater vents where likely everything was perfect, right? You were getting all the acids, and you were removing, and we were getting heat, and so it's probably a good thought experiment to think, perhaps that was why that was happening. And Andy, we've talked about this before. There were some archaic, probably heat vents that were underwater at one time up in the Arctic, and Andy and I got a chance to go right next to them and see them and go, wow. You look at it as an underwater vent, you're like, wow, this thing's now, first of all, it's now 330 meter above ground, or above sea level, and you're just like, wow, everything around that was potentially life back into the billions of years. Yeah, big, huge. That one vent that you guys went up to was spectacular. I wish I had that. I do have it here, but I can't. For some reason, I'm not able to share today. Anyway, we can move to the next slide if you're still here. Sometimes we can, because the file is so big, I bet it's not moving. Can you slip to the next file, possibly? Anyway, all right. Well, I'm gonna open my PDF. Yeah, anybody chime in while I'm looking for a way to do this. Go ahead, Siddharth. How are you? Good to see you.
Good morning, sir. I had a question regarding Olympus Mons on Mars. So So it's this large shield
Yeah,
volcano.
huge.
And so could it be the possibility that there was life at Mars and that was the reason that the life was wiped out of Mars? Or some say that it's a young volcano that's still in the stages of early development. So what's your thought on that?
Well, as a shield volcano, yeah, it's weird because there's no tectonic movement. The only thing that's coming from underneath, right, would be what was there already that might be influenced by either solar, likely solar pressures that might have actually caused those those environments to heat up like that. I, I think because there's no obvious tectonic movement, I don't know that we would get that kind of that turnover that you almost have to have in order for life to become to exist, right? I could be wrong, and these are again thought experiments, right? We're in this place where we know that we have to have tectonic activity and the turnover, but that's also the reason why we don't have any really obvious evidence from 541 million years ago or older of life, other than a few stromatolites here and there and some stones that fell from the heavens. So that's a good question. You see the size of that volcano and you know that it's some ridiculous 30,000 feet or whatever the number is. It's crazy as a volcano and mountain. I'd love to see some recent activity there. I know we've seen some volcanic vents, but we really haven't seen any magma flow. But that would be, that would be spectacular. It's nice to have the Mars surveyor there and moving around constantly, and has been for, I don't know, 20 years. Crazy it's been around that long. If anybody knows how we can change the next slide, that would be awesome. But it's my fault for some reason. I'm not able to get the slides to pull up. Oh, hey, thank you.
Sorry, I just got disconnected. So
okay, thank you. And I apologize. It's probably because these are so heavy in terms of amount of data. Okay, so this is life, right? As we know it, boom, here it is. All the volcanoes, all the tectonic motion, all of the solar storms, they're kind of killing the bad things or editing them genetically in such a way that they can survive and thrive in these really harsh environments. And so we needed those flares. We needed those early solar flares to hit Earth and to create all of these heavily radiated environments. If we hadn't have had that, right, we wouldn't be having these chats today. Those genetic edits really kind of indicative of how life and eukaryotes particularly kicked off. Probably underwater, near smokers, vents that are just constantly throwing all kinds of wonderful minerals that we need to survive. But the Mesozoic, that must have been a lot of fun running from those creatures, because there is evidence, right, of humans. In fact, I think I saw a 44 million year number just recently in a cave somewhere. They found some paintings that dated to that. But without the flowering plants and without all of the pollen, and by the way, we also were seeing evidence of pollen. We could see that in the in some of the stromatolites, oddly. We're lucky that we're only at this 120 years, right? Really, I know we've been, the great philosophers go back to the 1600s, but really, Earth and all of us collectively we weren't thinking about these things up until the early 1900s. It's amazing how far we've come in 120 years, 125 years. Which means exponentially, right? We should see some really significant things happen in the next, in these next few decades. hopefully sooner, because as I'm now over 60, I'm hoping that this last half of my life, we're going to see some really amazing things. So Mesozoic, I can't imagine living in the Mesozoic. That must have been you was just running and hiding, probably living in high altitude, probably up in those mountains back behind in the image. Uh, Probably the safest place, caves up really, really high. And yeah, so yeah, these are the theories that we are constantly thinking through. I'm sure all of us are, I'm sure all of us here that are interested in these types of things and joining today. But we can change to the next slide because I know we're running a little tight on time now. Yeah, here you go. And now we see these, right? We've got the mastodons. We've got plenty of those around. We've seen those. We're getting DNA from their tusks and their teeth, and now we're taking those genetic codes and we're replicating them. That's scary. I hope nobody makes a big, huge herd of mastodons that are starting to charge around New York City. That'd be fun. I'm in San Francisco, by the way. I'm not saying we want to see New York City full of mastodons, but that would be cool. Yeah, we can change to the next one because this is now we're in the Holocene, right? And the Holocene was probably, thankfully we have the Holocene, which is this moment of stability and our existence. And I say moment because geologically speaking, it is a moment in time, right? We're talking about tens of millions of years, and we're talking about planets 4.6 billion years. So moving on to Ragad and Kushi, what you were asking about, right? And I know Venus isn't on this list, but bye, Xenia. Thank you. Good to see you. Love you too. Be safe. Mars. This is a great. It's one of my favorite images of Mars because now we can kind of see the size of the ocean there, and we know that water is up underneath and stored as hydrates and likely in clay, and we know we can get water from clay, so the water's there. We just got to get below the iron, heavily iron crust. It's not iron like in molten iron, but it's ferrous, right? It's a dust that makes it look red. So I hope we get a chance to get below that. Everybody saw, I'm sure, that sulfur stone that Curiosity ran over and took an image of. And so now we know there's sulfur there. We know we can make oxygen there through the MOXIE. MOXIE is on Perseverance. MOXIE takes CO2 and turns it into oxygen with, I think, 800 C. It needs a little heat, but otherwise, good to go. I think they add an oxidase there too. So extremophiles here on Earth, we know we found Martian meteors here on Earth. That there was that one in 2000. When was that? Clinton's. Remember 2005 when Clinton came on and said we found life. Probably or probably not, but sure did look like it. If anybody saw that image of that meteorite with that, what to look to be a bacteria on the inside of it. Thankfully, we have robots there that are continuing to do the work for us. I think robots are probably in our near future. Dragonfly coming up. Mars Europa Clipper is going to fly around Europa for a couple of years. We've got. I think if we can get to Enceladus, I think there's a mission that's working on that. I can't remember. There's so many. Hard to keep up, actually. But we know that there was water there. We are sure of that because we can see the melting and we can kind of see those recurring slopes of water that's kind of moving down the slopes of the craters. And the good news is I think that's probably our next step. I don't think we should go. I'd like to say we could go to Venus, but it's probably too much technology and too much mass to move around right now. We need a propulsion technologist. So if any of you are working on propulsion, don't stop. Stay focused on getting us there fast and safe. Remember, we're not getting anywhere without energy. It'd be nice to have free energy too, if anybody can figure that out. We can move to the next slide. Oh no, we got disconnected again. Oh, there's Titan. Those are the methane lakes. Those are the mountains, the gorges. That you can kind of see that were formed by these, this motion of methane, liquid methane. And you're like, are you kidding me? Come on. Now, likely, when we're on Titan, we may very well find microbial life, because we know microbial life really enjoys methane. Now the pressure is so intense there. We might see some issues with that, but I don't know. I'd like to say, and I'd like to say that Titan may be kind of that Rosetta Stone that opens up kind of the answers. And now Titan's a little safer than Enceladus and Europa because the radiation environment's not super intense, still there, but it's not like Enceladus and Europa, which you're assured to die within minutes, if not hours, because the radiation from Jupiter is so intense. But yeah, Titan, please, if we get there, that's fascinating. Dragonfly did not get cut, by the way. The budget is still online for that. Good news is, I think we're going to build that device. I don't know how we're going to launch it. Rocket Lab, probably, or SpaceX. We can move to the next slide. Where are we going next? Oh, I'm going to start speaking about it until we move to it. So the next slide is about the Krebs cycle. And kind of to Rachel and I were talking about it earlier, this, without the respiration of these eukaryotes, right, we're not going to get mitochondria replication. And without replication of mitochondria, we don't have cellular growth or life. And replication kind of allows cells to repeat, and that repetitiveness, right, allows organs to grow and allows other things to grow, unfortunately. So the Krebs cycle is closed. It's probably the ultimate enclosed cycle. Takes all of the waste, uses it, spits a bit out, and I can share this. A lot of these images I just pulled and threw in, so they may be careful when you're sharing these slides. If you do, you might just go and see if you can't find the owners of those images. Because we're in an educational environment, I don't have to necessarily to credit those images. If it were outside of education, you do have to. So the cells themselves, you think about the sun, right? We get blasted every 11 years. Probably, I think that number was not every 11 years in the early Mesozoic, and now in the Halcyon, or not Halcyon. Anyway, I'm drawing a blank. So Holocene. So we were getting blasted pretty regularly. And so the mitochondria were like, what's going on? And we can't replicate in these environments. So that's when we finally got stability of Earth's atmosphere, and we got a magnetosphere that was nice and strong. And we oxygenation events. The great oxygenation was the reason why we're all having these chats anyway. This guy, this Krebs. I think he was in the 1960s, 1962 to 64. Everybody considered him a quack and a kook. And now I'm like, this person was on to something. And because if we want to live on another world, right, we have to have a closed environment. It has to be closed loop. How are we going to take our waste and use that waste and not, poison or potentially ruin another planet? I'm not saying we've ruined ours, but certainly we're not on the correct path. Yeah, the Krebs cycle. If you guys get a chance, dig into the Krebs cycle. You'll be endlessly fascinated with that. We can move to the next slide. So I want to leave 20 minutes for everyone here to have a proper chat. So sorry, I wish I could figure this out. I apologize. Oh, thank you. Yeah. kind of moving through the citric acid and how it works in the Krebs cycle, and aerobic respiration. So the acid themselves, just we need an acidic environment to get the oxygenate, and so without that, we're not going to get these pyruvates, right? Pyruvates, that to me was also a bit of a Rosetta Stone, right? And that to me said, hey, we've got these primordial metabolites that are out there floating around, in this case in the oceans, and yeah, they're early life. They're how the eukaryotes. This is that transition from prokaryote to eukaryote. Again, 500 and something million years. What are you kidding me? Go back to again to that 3.6 billion year range. This place must have been hellish to hang out and be a cell. And you weren't even, there was no way you were surviving. So chemosynthesis, if anybody's really keen, Nick Lane, if you get a chance, read some of his books. He's got several out now. Most of his papers are spectacular. He's out of University College London, and you'll really get a kick out of digging into the Krebs cycle and these early metabolic kind of characters that allowed us to be here today. We can move to the next slide. This next one's really cool, Andy. You'll like this one. The smokers. Yeah. So these hydrothermal vents, are without a doubt. Well, there is some doubt still. Pangea. You can think through how, and what do they call it? Maybe we were seeded with another asteroid or other meteorites or meteors. And those could have been those early seeds of life that kind of spread out like we do when we're growing our corn or our rice. But, who's to say, right? The early Earth was so crazy and incapable of life. Kind of makes me think that maybe, panspermia might have happened, right? That's a possibility. But I do think that all the chemicals were in place at these hydrothermal vents, these black smokers particularly. The black smokers are even a little more fascinating. So if you get a chance, dig into those too. You'll go down the rabbit hole pretty quickly. I do every day. Andy knows that personally. So, methanogens, or which really are just a methane creature, and these methanogens or methane, we needed it and we had to have it. Now we need less because it's a terrible gas in the atmosphere. But yeah, so do get a chance to look into chemosynthesis. I'm happy to have additional conversations in other classes about this. But we can move to the next slide. There we are. How are we going to find all this out? We need to get out. We need to get out to other places. Apologies. Pop around, get into these analog environments, do some really deep research. So Andy and I were up last year in the Arctic, and I was again there this past summer. Andy, you're coming again next year. We were. There are only 13 types of 13 species of life as we know it up there, and that's it. It's incredibly barren of life there, but it's there, and still you can turn a stone over and see evidence of life. And now I did turn stones over and think, oh my God, I'm turning a stone over that's been laying like this for 35 million years. Should I be doing that? And I was definitely very concerned about that. Because it's also a place that's so pristine. Post the asteroid or the meteors, sorry, possibly an asteroid that broke into the atmosphere, it hasn't been really disturbed. And every place I stepped, I felt like I was the first human to step in that spot. And that's probably why I like going up there. Of course, I'm deep into cyanobacteria research. I'm using it as a feedstock for plants to bioremediate really bad soils. So if you've got really bad soils and you're maybe in a river delta that's next to an ocean, right, with really high salinity and or basalts and things like that in the soils, I'm finding evidence of through my research, which are in these tents behind me here in the lab. These tents have shown me without a doubt we can use cyanobacteria as a bioremediation for really bad soils. I want to take that to Mars and kind of improve Martian soils, Martian regolith. Same for the lunar surface as well, by the way. And so that I've been studying that for the past year. I got funded in late 23, and so I've been doing it really for a year now. So yeah, oh my God, I can't wait I'm trying to get to the Atacama Desert next May. I'd like to get up there. Yeah, good, thank you. Missions that are coming up, right, where we already know Perseverance is out there. We've got ExoMars, it's on the way. It's going to be a kind of a subsurface drill. I think it's going to get down to 10 meter. Dragonfly, of course, and we can move to the next slide too. Dragonfly, oh my God, I can't wait for that. I'm really hoping that's as exciting as it. And here's this next slide is the Dragonfly, and we can move through that as well if you want to keep going. I want to open it up to questions sooner than later. Can we flip to the next slide? Brilliant. So I don't see humans getting to Titan safely unless we bring a really heavy pressurized vehicle. Pressure is not going to be a problem there. Of course, we want to maintain our ambient pressure that we want, which is 14 GA, right? So yeah, here we are. I think we're on the cusp of finding evidence. I think it very well could be in the methane lakes of Titan or the ocean world of Enceladus. Everybody's seen those plumes, and we know that's water. So I think that's also fascinating. We can move to the next slide too. Yeah, why? Okay, boom, here we are. Honestly, this is where theory kind of takes over. Expanding our knowledge, our knowledge of biology is not rudimentary anymore, but it was up until about 40 or 50 years ago. How planets formed, again, only 40 to 50 years of kind of evidence of how angular momentum worked and how these rubble piles turn into, fortunately for us, turn into asteroids and become kind of these panspermia seeds that move out and through our universe. And then as Earth and the planetary, our solar system moves through the Sagittarius arm, and as the Sagittarius arm moves through other perturbations that are out in the universe, maybe those are also affecting us now. There is evidence of, and a recent paper suggested, I had suggested it many years ago, that as the Sagittarius arm is moving through previous galaxy mergers, those galaxy mergers likely had other chemicals and other elements that might have been part of the reason why we are here today and having these conversations. We might actually be very special in that regard, and certainly nobody's reached out to us, but of course, we haven't been alive long enough and listening long enough to know for sure. We can move to the next slide. Can imagine, are we alone? And we find out we're not alone. Whoa, I can't, I don't know. Would that be total chaos on Earth? Maybe, probably not. Hopefully not. We can move to the next slide if you want. Yeah, this kind of goes to that same conversation I was just having. Theoretically, there are all these chemistries that can happen as we move through the solar system and as we move through the galaxy. All of these things, we can only surmise what's going on. We can only guess. Even if you throw it into some of the most powerful computers on the planet, we're not getting the same detail and the same information every time. It's always different, which is what I do think that if we get quantum computers and we were able to get a kind of a hive of quantum computers, I think that could be also a pivotal moment in our near future, very near, by the way. And then finally, last slide is questions. I'll open it up. We've got 15 minutes. A question not asked will remain unanswered. I don't know who said that, but it sounded good. Yeah. Go ahead, Andy, do it. I'd have to. Am I sharing? I'm not sharing anymore, am I? Hey, Andy's going to share his screen. If you want to stop sharing yours and then let him jump in, he's going to show us a couple of images of our mission up into the Arctic. Yeah, there you go. And that's it. So there are fossilized lichen that are around the base, or maybe even embedded in the inside of that hydrothermal vent that we need to get to. And we have to get permission from the Canadian government. Well, not anymore. Now it's just the government, the Nunavut government, which is up in the high Arctic. But there very well could be, fossilized remains of who knows what in there. And but it's rare to find them above ground, right? Most of the time they're so far undersea that you talk about taking risk, and your life in your own hands is getting underneath that amount of pressure when you get down to those abysses of research. God, can you imagine? Oh, yeah, Andy, I'd really like to get into that, but I think we have to get permission. So I am going to ask this year if we can get a piece of it. Yeah, I know. I would be really happy to do that. Anybody else? Life everywhere. What's on your research plate? What is everybody working on? Well, we can talk about exoplanets real quick. I can kind of go into that. We're at 5,600 exoplanets now, and because we're really flying along in that endeavor, exoplanets could be a really amazing source of research. If you guys are anybody doing that, it's an amazing field. I'm always challenged when I start talking through exoplanets. I am a professional astronomer. I partially run a radio telescope. I get radio telescope time on it. At Pisgah National Forest. It's called the Perry Radio Telescope, PARI. I also have time on 4 university grade telescopes, and I get every opportunity I can. I get in and open up and look at other things in the universe. Go ahead, Kush.
Sir, what did you work on exoplanets, like spectroscopy or what? Like
yeah, good question. No, I'm only verifying and confirming their existence. So I took most of so we have a team, and I run the team. We have right now we have 5 members. They are finding host stars that are within, I'd ask them to look within 150 light years. And then within that 150 light year, I'm hoping to find planets that are within their habitable zone of those stars. So I'm avoiding looking at really big stars. I'm hoping to look at kind of, Earth size, or excuse me, our sun size. So we're narrowing it down to that. I also am having them look at any flaring stars that are obviously flaring. But otherwise, it's taking TESS and Kepler data, and even going as far back as Hipparcos, and confirming those exoplanets. We only have most of TESS and Kepler, and even Gaia are only single one-offs, right? So then our job is to go back in and make a confirmation of that. And then at that point, I can ask for extra time. Like I've just asked for extra time through Keck to observe an exoplanet that I found with another colleague, but it's 1,800 light years away, which is just a bit too far. So yeah, good question now.
So it's a silly question, but did you find any planet that have habitability? Confirmed it?
No, no, they're all too close, and they're all super Jupiters or super Neptunes. Yeah, no, nothing. I haven't found anything rocky yet that would be considered a habitable spot. I know James Webb Space Telescope has, and so now they're also seeing an atmosphere on one of those that they've located, and that's the one, I think, the paper that came out last week. You may have seen, or I wish I had it here pulled up. I'm happy to share that after the conversation here. I'll drop it in Hex-Star, and you can pull it up. But that just released, and in fact, it's pre-release, so it's still being reviewed, peer-reviewed.
Okay, sir.
Yeah.
So you also work on biology. Like I have seen your paper about myomagnetic fluid and other than that. So yeah.
It's fascinating that so here, one of the technologies that I'm working on, which is right here. This is an electromagnetic field generator, and I'm trying to line it up in a horizontal pattern from X to Y, and that device, it just, all I'm trying to do is move ions. I'm trying to keep ions moving and directionally.
Mm-hmm.
When we're on the lunar surface, right, or when we're on another planetary body that doesn't have a magnetic field, what I'd hope is that we bring something with us, right, that allows. So you think about our bodies. Our bodies have evolved over these 500 million years in a magnetic field, and that magnetic field is at about 0.03 Tesla, or even less if you use something other than Tesla as a measurement for magnetism. So Gauss is 0.003. Yeah. I didn't see the comment. Sorry, I will go back and look at that. You bring up a really good point, right? We were going to have to protect ourselves somehow. I don't know that I can build something that can deflect high energy particles. I know I can, and I've proven that, and it's been proven already in the lab out of Leicester University, and I forget the PhD there that has done the work. Ruth Bamford, Bamford. Bamford. Ruth has figured it out, right? She built a plasma wave, and that plasma wave can take an HEP, a high energy particle, and deflect it around you. In my case, I'm just trying to keep your body alive. Your body is evolved in a magnetic field. Well, there are no magnetic fields to speak of on the lunar surface. There are anomalies here and there. Same for Mars, anomalies. Let's bring it with us. Let's create a really low energy magnetic field that can protect our cellular structure and keep it working, right? We're talking, and this goes to the Krebs cycle. So the Krebs cycle has to have a magnetic field around the cellular membrane to allow for transpiration, right? Without transpiration, movement of the chemicals in and out of that cell, your cell dies. So really, we're going down to simple technology that's been developed since, I mean, we can go all the way back to Lemaitre was talking about magnetism. And then, of course, the Irish fellow, I forget his name, who was digging deep into magnetic field theory. Cole and I, the paper you're talking about, Cole and I have been talking about how it affects cellular membrane, our eyes. We're going to have an electromagnetic field. It doesn't have to be crazy powerful. It just needs something to allow our cells to continue to develop. And Rachel, kind of to your point, Krebs cycle in a reverse Krebs cycle, it forms cancerous cells. And so how do we what field do we need to be in to where we don't allow the Krebs cycle to reverse in our own body? So it's kind of creepy to think that there are things out there that we know the technology exists now that we could use, and we're just not talking about it. So Cole and I have been talking about that. I think Kushi, you might have seen early on. We started in 2020, and we've been talking about it pretty much really just not all the time, really, for the past 4 years. Now almost 5, because he's working on another paper that he's presenting in January, and it's the same thing, just keeping our magnetic field with us. So sorry, just Rachel, I'm looking at your note. I have to make a note of Viking. Yeah, Viking was questionable. That Viking principal investigator went to his grave arguing that we found evidence of macrobiotic life there with the Viking mission. And he, I don't know that the data was that conflicting also. I think it was NASA saying, hey, we've got one set of data that say that's not possible, but his evidence was overwhelming. I don't know if anybody knows that whole story, but that PI, he to the last dying breath, he was arguing that we weren't thinking about the right thing.
Thank you, sir.
Yeah, of course, anytime. Anybody can reach me anytime. I'm Andy knows this. I'm highly available. LinkedIn, email, you name it. Phone calls. I'm happy to get on an early call too for those of you, because it's getting late where you're at. Kushi, go ahead.
Sir, could you please share your email ID with us? It would be thankful for you.
Yeah, it's late where you are. I appreciate you staying up. There you are. So I have a dear friend, really a very close friend, whose mom lives in Colombo, and so we. Yeah.
Sir, we can see that. We can see that. Thank you.
Oh, good. Awesome. Of course. Yeah. Reach me anytime. Again, a lot of the astrobiology work that I'm doing is up in the Arctic. I do want to go to the Antarctic, but I don't know that the Antarctic gives us kind of the detail that the Arctic does. So yeah, isn't it great, Rachel, that we have students out there that really care about these things? It's fantastic, actually. But I'm in Sweden next week. I'm speaking at a conference about the Mars analogs, and that is next Friday, Saturday, Sunday. And then I'm popping up to North Dakota on the way home. And then North Dakota, again, speaking about analogs. And it's also where I'm working as a GA. So if anybody knows, graduate assistant. And yeah, so reach me anytime. I don't want to take any more of your time. It's probably nearing 11 o'clock for most of you. So PM. And by the way, if you're asleep, it's okay. I get it.
No, sir, we are not sleeping. It's so nice to interact with you.
Yeah, it's wonderful. I appreciate your passion and enthusiasm. I can sense it in your voice. So.
Sir,
That's it from.
I am from India, and I am currently in master's degree. That is master's in astrobiology and space science from MIT University, Mumbai. So yeah, it's
Awesome.
so quite fascinating that you are talking about astrobiology. So I just got to know about that and just went in registration.
Hey, frankly, all I want to do, yeah, Rachel, of course, thank you. All I want to do is to keep you, just keep your mind open, right? I think that's one, because I'm fairly new to the industry in terms of new to the industry. I mean, I'm only 5 years in industry. Before that, it was all theory and education, and I do think that with a pair of open eyes, you see a lot more, right? And so I find myself being more interdisciplinary and multidisciplinary than I do just astrobiology. And I think there's plenty of room for multidisciplinary folks out there, particularly mission planning, mission management, project management, which is where we really need highly educated people leading us. So yeah, there is a place for everyone. Yeah, of course. And Rachel, you're right. Dreaming about space exploration alone, it allows us to manifest. Anyway, reach me anytime, folks. And Andy, love you. Good to see you always. And
likewise, awesome talk, Terry.
Yeah, awesome. Yeah, I really appreciate you always. And I'll see you next week.
Thanks. See you.
Sunday. Yeah, but we'll see you. Everybody be safe. And Ananya, microbiology. Whoa, that's a good one. They go hand in hand. Microbiology, astrobiology. All things small. Again, you want to dig into DNA too. DNA, RNA. I've really been diving deep into that lately. So awesome. I'm gonna get my day started. You guys get some rest. Rest those beautiful minds.
Thank you, Terry, for the wonderful presentation and your great insights. And thank you to everybody else for joining the session. Good night.
Absolutely.
And
one
have
last
a nice
question.
day.
Thank you, sir. Good night.
See you, everyone. Take care. Bye.